Yeah, uh, welcome everyone. I hope I'm audible. So, in the last class, we covered discrete one-dimensional phononic crystals. Um, Phononic crystals are nothing but mechanical metamaterials. So we call vibrations as phonons. And crystal is just a repeating pattern. So mechanical metamaterials, phononic crystals, one and the same thing. And then we said we elaborated on what is 1D. So we see that 1D basically means that there is 1 degree of freedom inside the unit cell. So let's say this is one unit cell and it is connected to the next and the previous unit cell. So if this is I, this I plus 1, I minus 1. So, so inside this unit cell, the total degrees of freedom will be 1. Of course, if you consider an infinite crystal, then the total degrees of freedom are infinite. But, uh, but by by analyzing it for 1 degree of freedom, we can get the behavior of waves propagating in the infinite chain. So that is going to be essential, right? So by 1D, 1D is the simplest system. For a lot of phenomena that we observe here, it will be generalizable to a lot of other systems, 2D, 3D. But it's important to note that the extension of this, the let's say uh, the periodicity, rather, let's say spatial periodicity is only in one dimension. So we call it a chain. Uh, this there could be material in the other direction, but there may not be periodicity in the other direction. Even then, it's a 1D. Uh, even then, it's a chain essentially. So 1D does not mean uh, like a literal chain. When we say a chain, like we're talking about in how many directions is there periodicity. There's periodicity in, yeah. So so the question is, how so that is something to consider. The next thing is within each unit cell, how many degrees of freedom are there? So, so this is periodicity in one direction, and in each unit cell, we only have 1 degree of freedom. So, so we call it monomer. Mono is 1. So this is the unit cell. It's connected to the adjacent unit cells, and we see that. So now, what we did here was we we want to know how a wave will propagate. We need to start from equations of motion. And how do we get equations of motion? So in the unit cell, we have a mass. It's connected by some springs. So if there is some motion, those springs would naturally apply some uh, forces. So the spring on the right applies this force, spring on the left applies this force. It's based on the displacement of the adjacent degrees of freedom. And then here we have written net force is equal to mass into acceleration. So, so this is the equation of motion. However, so we have terms like ui minus 1, ui plus 1, right? So I think this is the correct equation. Then what we observe is that if the solution is assumed to be harmonic, like here we see that ui is, let's say, some u naught, which is some amplitude, into e power I into some phase. And within that total phase, we have terms like qx minus omega t plus phi, where phi is the additional phase and q is the wave number. Uh, yeah, here q is the wave number and omega is the angular frequency. And x is the x coordinate. So it's a coordinate, it's not related to displacement. Right, so we can write it in this form, ui. Then what is ui double dot? If you see, you take double derivative, you will get minus omega square outside. So essentially ui double dot is equal to minus omega square ui. This is typical in harmonic systems. Further, we apply the block K period boundary condition. So what we do is, by using the block K periodic boundary condition, we are able to relate ui plus 1 to ui and ui minus 1 to ui. And by substituting the coordinate instead of, say, let's say x, we have x plus a or x minus a. If you substitute that, we get this e power iqa outside or e power minus iqa outside. That's how we can relate adjacent unit cells with the main, the primary unit cell. So by doing that, what we have done is, in a way, they are telling that although there may be infinite degrees of freedom in the entire crystal, the entire crystal will have infinite degrees of freedom, but by relating the displacement profiles of adjacent unit cells, by connecting them through this wave number uh, induced phase difference. So basically, we are saying that the phase difference between this and the next one depends on the wave number. We are able to write our original equation in this form, and then further, if we substitute, if we write e power iqa in terms of cos and sine, we get the equation something like this. Further, further we see that this 2k to 1 minus cos qa, like this can also be written in terms of sine square. So so what is omega? If we find out, we get omega is this. Um, Omega square has been, like, we've taken square root, but omega cannot be negative, so we have neglected uh, the negative solution of omega. This is the positive part, and we see that it's a relation between q and omega, whereas the other terms are fixed. A is the lattice constant, the distance between the lattice particles, unit cells, basically the size of the unit cell. The spatial periodicity is dependent on A, the length. K is the stiffness and is the mass. So if you increase the mass here, then the omega will reduce. If you increase the stiffness, omega increases. So yeah, similarly, if you increase A, then you'll see that so omega is again increasing, depending on the range, of course, of wave number that we are talking about. Right, so this is the cutoff frequency. We saw this pattern repeating. So what we notice is that because of spatial periodicity, right, in the crystal, we see some periodic behavior in the wave number direction. So wave number is like 2 pi by lambda. So it's like 1 by lambda, right? So the dimensions are 1 by length. So this space is called reciprocal space. And the wave number space is called the real space. And the real space belongs to lambda reciprocal space belongs to wave number. Okay. So if there is periodicity in the real space, it will show up as periodicity in the reciprocal space. So that's interesting. Just like we said that you don't need, because of periodicity in the real space, you don't need to analyze each and every unit cell. You can just analyze one unit cell. Similarly, because of periodicity in the reciprocal space, you don't need to analyze each and every zone here. You can just analyze from here to here, and everything else is just a pattern. It's a repeating pattern. It's a crystal. So, what do we call this space? We call this space the first dimension. I think I have to mention here first dimension of this space. And further, we say that because uh, because there seems to be some mirror symmetry along this line. What that indicates is that waves propagating in to the right and waves propagating to the left, they both behave the same. So so the this is called reciprocal behavior. Like if there's a wave propagating from right to left and from left to right, it will behave the same. So in simple mechanical systems, the behavior is reciprocal. In certain systems where there may be energy loss or energy gain, we may see non-reciprocal behavior. but that is not considered here for now. So, so since we said that this and this are the same, like there's a mirror symmetry, we can just consider this part to analyze what is going on. What is right? So just this part we call it the irreducible Brillouin zone. You cannot reduce it further. Yeah. Then then we talk about what is omega cutoff, which is a cutoff frequency. So above this cutoff frequency, stable propagating waves cannot be sustained. Like if there is a wave and you just let it be, it will not keep sustaining. It'll die down spatially. It'll decay, not in time, but in space. How do we know it is not in time but in space? Well, so what really happens is in this band gap region, so we call this band gaps. Right? This is a pass band. Everything above it or even below it, you can call it band gap because sustainable propagating waves can be there. So in the band gap region, yeah, in the band gap region, we have complex like wave numbers. So why is complex wave numbers leading to unsustainable non-propagating waves? We see that Q is equal to alpha plus I beta. Let's say we break the complex number into two parts. Then instead of Q, if you write alpha plus I beta, then you can take this beta and x out, and then you'll see that e power minus beta x. That basically means that with space, there's a decaying envelope. That means it's not a sustainable wave. Similarly, what happens if omega is complex? Then there is going to be decay in time. What do you call decay in time? You call that dissipation. So why are we talking about this? Is that yeah? So that means that this is the highest frequency at which the passband exists. Above this, there is no propagating wave. So we call that frequency cutoffs. Then yeah, so and depending on what is the alpha plus I beta, the beta values, the decay profile in the band gap. So this plots the imaginary part of Q, the dotted line here. So the decay profile is plotted there. Right, then we speak of Bragg scattering. What is Bragg scattering? Then we talk about X-rays. If there is a crystal, if there is X-ray, and then we say that the reflectance is really, really high at some particular angles or some particular frequency of X-ray. So, so that is used to study the structure of the crystal. That studies the spacing and things like that. So why is it happening? It's happening because there is something called Bragg's condition, which is satisfied. And what is Bragg's condition? Where lambda is equal to 2a in a 1D chain. Lambda is equal to 2a is the Bragg's condition. So, so if this is satisfied, band gap will open, even just like in the X-ray. When you have high reflectance, that means very low transmittance. that means that's a band gap because it's not propagating. The wave is not propagating. So when lambda is equal to 2 is satisfied, the wave is not propagating. So if you take lambda is equal to 2a and then you calculate the value of wave number appropriately, you'll find that wave number is pi by a. So the band gap should start at pi by a. Do we notice that? Actually, that's exactly what we noticed at pi by a. Like till there, it was somehow propagating, but after pi by a, it cannot propagate further. So yeah, it comes back. So at this wave number and frequency, that forms a cutoff. Similarly, minus pi by. Right, so we understood the basic concepts of the first the monomer. Then we moved to the dimer case, where di means like two. So inside this unit cell, there are 2 degrees of freedom, one for each particle, and these particles are constrained in the horizontal direction. And yeah, so this is a general dimer where let's say you have mass m1 and then mass m2. Then in between them there is a stiffness k1 and then outside there is a k2, and if this is k2 then this also has to be k2 because this m1 connects to the next m2. That means the m2 must connect to this m1 with the same stiffness, right? So if somehow this k2 and this k2 are not same, then the periodicity would not be only 2 unit cells, it would be higher. Then you have, it would not be a dimer, then you'll have to look at different, yeah, different this thing. So that's a general dimer, and then we have a stiffness dimer and a mass dimer as special cases. So what's a stiffness dimer? A stiffness dimer means that the mass is not dimerized, which means mass is just m everywhere. So that's, you know, like a monomer. Whereas the stiffness is like K2, K1, K2, K1, K2, K1. So the stiffness is dimerized. So this call we call it stiffness dimer. Similarly, we have a mass dimer. That means mass is dimerized, which means M1, M2, M1, M2, M1, M2. Whereas if you have stiffness K, like the K is not dimerized. K, so K is not very as if it was a monomer, but it's the mass which is causing the overall unit cell to be dimerized, and the stiffness which is causing the overall unit cell to be dimerized. So I think first we took the example of a mass dimer and draw the unit cell, then call this degree of freedom U1 of I. This was U2 of I, but I is the unit cell, so the central unit cell, and then U1 and U2 correspond to M1 and M2. So the next particle is this M1, so it has to be U1, but since it's the next unit cell, it is I plus 1. And here it's M2, so it has to be U2, but since it's the previous unit cell, it has to be I minus 1. So these are all the 4 degrees of freedom that should be sufficient to write the equations of motion. So what we see is that if you were to write the equations of motion, then you'll see uh, like for each mass you could write two free body diagrams, and there are two degrees of free independent degrees of freedom. So you'll get two equations. This is the first equation, uh, and then this is the second equation, right? So So this is nothing but f is equal to ma on the first free body diagram of m1, and this f is equal to ma on m2, the Newton's second law, right? And then appropriately we have converted the double dot into minus omega square u I uh, format, which is characteristic of harmonic motions. So, so we get this. Then, yeah, then further we see that since we have two equations, like this is one equation and this is another equation, so we can combine them in this format, like u1, u2, u1, u2. These are the degrees of freedom, and then we can write it in a matrix form. This is the mass matrix. So if you multiply this with this, you get two two rows of equations, sort of. Similarly, this is stiffness matrix. So if you combine both, you'll get this matrix. Now, so this into this table. So
Hey, Shrikant.
yeah, I was just recapping uh, how do you write the equations of motion for 2 degrees of freedom, and how do you combine the matrices and then take the determinant. So yeah, so here, so what
Got
we
it.
say is, yeah, what we say is u1 and u2 are, let's say, your degrees of freedom. So if you take the whole determinant, then you'll have, and the whole thing is equal to 0. That means that either this or this is 0. So if u1, u2 is 0, that means that the masses are not moving at all. Then we are not talking about motion that we aspire to capture. That would be something trivial. So we want characteristics of wave propagation to be captured. So u1, u2 cannot be 0. That means this matrix, the determinant of this, has to be 0. So if that is 0, then this is basically the determinant is equal to 0. And then further on simplifying, we see that um, it's a quadratic equation in terms of omega square. So omega power 4 and then omega square, and then there's no omega here. So so this is a quadratic equation in terms of omega square. So so we know how to solve quadratic equations. We'll use the formula minus b plus minus square root delta by 2a. Delta is like b square minus 4ac. So we apply that equation, and then we see that there's a plus minus here, which means there are two values of omega squares. So yeah, so and then further so we'll get two bands, um, and then since we get two bands, yeah, since we get two bands, then the cutoffs have to be, for each band you'll have two cutoffs, one minima, one maximum. So typically, like one one of the cutoffs will be at omega is equal to 0. You can just find that out when you put q is equal to 0. Then what happens is, uh, when cos of 0 is 1, so 1, this bracket, this entire thing disappears, and then this is nothing but this. So this minus the same thing, so that means omega is 0. And the other one is this plus the same thing by 2m. So that will be the other value. And then we have to put q is equal to pi by a. So when you put q is equal to pi by a, we'll get the other two cutoffs. So here we are assuming that the cutoffs are either at q is equal to 0 or q is equal to pi by a. So q is equal to 0 is completely in phase, you know, because when q is 0, then That basically means the wave number is zero. That means wavelength is really large. That means the phase difference between adjacent unit cells is zero. Whereas Q is equal to pi by A, that means the adjacent unit cells are, you know, out of phase. Yeah, so this is out of phase. So basically, the Brillouin zone can be thought of as a variation from in phase to out of phase. And then again, it will go from in phase, out of phase, in phase, out of phase. That's why this is enough to plot everything, as long as we're talking about reciprocal systems. And here we discuss this point that long range interactions, uh, said long range interactions can induce local um, maxima, maximi, or minimi. But this is inside the irreducible relevance zone. But it could also be global. We don't know. So we have to verify that for each system. So what? So if there are no long range interactions means that you're skipping one mass and then connecting to the next unit cell. So say all the connections are between, let's say, unit cell 1 to direct unit cell 3. So if you have that level of connections, then that's long range connections. So uh, yeah, as long as that is not there, then maximum minima are going to be at totally in phase, well, or totally out of phase. That's what we had covered so far, I think. Then we speak about this band gaps, uh, and then we speak about band folding. So yeah, so this was the recap. We'll take a 5 minutes break. I think meanwhile, you can ask some questions.
No, no, it's clear.
Clear? Okay. तूने फुटबॉल देखा है ना कभी? उसमें टाइम वेस्टिंग टैक्टिक्स देखे तूने? हाँ। इतना कौन वेरीफाई करेगा? हाँ, आई कैन ट्राई मे बी। यार वो हाँ, थोड़ा ढूंढना पड़ेगा। है सब कुछ, थोड़ा सा ढूंढना पड़ेगा। कल सुबह कर सकते हैं, रात को एक बार देख के। आज मोस्टली बस नॉन चीजों में टाइम पास करूंगा। एकदम कंटेंट एकदम सामने पड़ा है टाइप्स। राजेश सर को कार्ड मार देंगे। क्लटर तो लग रहा है नोट्स। हाँ, these are in depth है। हम्म। हाँ, कंटिन्यू भी करूंगा। हम्म। हाँ, मतलब क्रिस्टल्स आर ऑलरेडी डिस्क्रीट एंड क्रिस्टल्स पे है थोड़ा काम। सर का पर्सपेक्टिव वेव प्रोपगेशन इन सॉलिड्स पे था, तो वहां पे पहले कॉन्टिन्यूम में काम हुआ है ना। तो आई थिंक वो है कि तुम क्या पर्सपेक्टिव लेके आ रहे हो। और ठंड कैसी है? कानपुर वाली? लग गई आदत एक दिन में। ओ। तो क्या भी चल रहा है वापस? ठीक है, चल फिर फ्रेश फ्रेश हो जा। मैं स्टार्ट करता हूँ। हाँ, चल ठीक है। और क्या कर रहे हैं बंडल लोग, कृष्णा विष्णु क्या कर रहे हैं? ठीक है। बस, नहीं मैं चाहता हूँ कि सबकी एक एक बार तो अटेंडेंस हो, ताकि मैं बोलूँ कि सबने अटेंड किया है भाई। ठीक है। ओके। हाँ। ओके। Yeah, uh, welcome back. So, this is what we were discussing. Now that we have seen, like, start recording again. Wait.